Hello, this is the second part of our recording, chapter 4. We have, like in the slides, 40 pages left. We are going to go through them right now, and after this I'm going to send you some solutions from fall 2019 lecture notes. We are going to solve some problems over the things that we covered. They should be very helpful to you. Here we have the second derivative test for local extrema. Before that we have second derivative test for concavity. Now this is for second derivative test for local extrema. So we have two types of second derivative test. Okay, be careful about that. This second derivative test is going to say something about the local extrema, local maximum and local minimum. Alright, and let's see. Here we assume that second derivative of f is a continuous function on an open interval that contains c, the point c, and we have a local maximum at c if the first derivative at c is equal to 0, in other words c is a critical number, and also second derivative at c is negative. Okay, we have f local minimum at c if c is a critical number, which means f prime c is equal to 0, and the second derivative of f at c is positive. And on the other hand, first derivative at c is 0, second derivative at c is 0, which means c is a critical point here, but the second derivative is neither negative nor positive, then the test fails. So it doesn't say anything to you. So it doesn't say whether there's a local max, local min, or neither. It doesn't say anything. So be careful about that, okay? So let's work on that. Look, let's say at this point the derivative is 0 at this point, and second derivative is negative. Okay, second derivative is negative means what? Second derivative is negative at this point means it's concave down. Whenever you have a concave down position and whenever the derivative is 0, it is obviously a local max. Look at that. And similarly, again, c is a critical number here, which means the derivative at c is equal to 0. And second derivative is positive, which means the graph is concave up. So we expect, we get that we have a local minimum, as you would see here, at c. Okay, so as we said here, you can see the picture and how second derivative test implies local max and local min here. I think this is an example of this question. As you would see, we have this function x to the 4, y is equal to x to the 4 minus 4x cubed plus 10. And what we do, okay, we take the derivative, and you don't see the derivative here. Let's see, the derivative is 4x cubed minus 12x squared is the derivative. And then what you would do, you would just look at the roots of that derivative. You would get 0, 3 as the roots. And then you build this table. This table is first derivative test table. See, this is sign of f prime and behavior of f. And this is the second derivative test table. This is the sign of f double prime and behavior of f. Because you can get information about the behavior of f, the graph of f, by looking at the sign of f prime and sign of f double prime. So these two tables are important. This is just a summary of that. And if you take the first derivative, you have 0 and 3 as the roots. If you take the second derivative, you get 0 and 2 as the roots, and you put them in here too. And you look at the concavity, and you combine these two tables, and you get this picture. Whenever x is 0, 2, 3, etc. So whenever x is less than 0, function is decreasing because we get it from here. And it is concave up because the second derivative is positive. We copy it down here. Between 0 and 2, we just look at in here, it is decreasing and concave down, we write it down. Between 2 and 3, it is decreasing, however, concave up, we write it down. Whenever x is bigger than 3, it is increasing and concave up, we write it here. So this part is the summary of the picture, and we look at in here to draw, to get this graph. Look at this graph, okay? So 0, 2, 3. Okay, before 0 it is concave up and decreasing. between 0 and 2 it is concave down. Okay, between 0 and 2 it is concave down, and it is concave down and decreasing. Between 2 and 3, as you will see, it is concave up and decreasing. Between 3 and further, it is concave up and increasing. So you just draw this picture according to what you got here. This is the summary of everything, so you should do that. Okay, so here's a procedure for graphing y is equal to f of x. First of all, what you're going to do, the domain of f is important, domain of f. You just identify it. And if there are any symmetries for the curve, just you state the symmetries. Is it symmetric with respect to the y-axis? Is it symmetric with respect to the origin? You just check that. In other words, you can just check whether the function is even or odd. And then you're going to find the derivatives, the first derivative and second derivative. You're going to find critical points of f if there is any. And then you're going to draw the first derivative test table. And you're gonna use the first derivative and express the behavior of the function. And then you're gonna state where the curve is increasing and decreasing. Okay, this is the first part. And then next you're gonna use the second derivative of f. You're going to find the points of inflection if any occurs, and you're going to express the concavity of the curve. You are going to do this by building up the second derivative test graph, and there you're going to express the concavity where it is concave up, concave down, and afterwards you can just summarize in one table. First derivative test table and second derivative test table in one table, as we did in the previous example. And then asymptotes are also important. Identify the asymptotes if there are any. Maybe sometimes there's none. However, if there are some, then you just have to identify and express it and put it on the graph. And then we have the intercepts, x-intercept, y-intercept. In other words, you have to state where the graph intersects the x-axis and where the graph intersects the y-axis. You just put them on the graph and you're fine afterwards. Okay, so that's how you would do it. And next, let's see. These are examples where the graph of this function, x plus 1 squared 1 over 1 plus x squared. I want you to look at the horizontal asymptote, and I told you how to find it. You will just take the limit of this, and the limit goes to 1 here. So we have horizontal as x goes to infinity and negative infinity, right? We talked about this, and I had a recording which shows you how you would do that. You just take the first derivative, second derivative, you build the first derivative test table and the second derivative test table, and summary of the two, and you're going to get the point of inflection. This is where the concavity changes. Look here, we have this is concave down and this is concave up, so this is point of inflection for sure. This is concave down, this is concave up, so this is the point of inflection as well. We have local max, local min here at -1 because the second derivative is positive here, so it is concave up. This is the second derivative test gives us as this local min. Second derivative test gives us local max here because look, the graph here is concave down. Okay, second derivative at 1 is negative. Positive. Therefore, this is a local maximum. Pardon. Let's see. Second derivative is negative. I'm sorry. Second derivative at 1 is negative, so we have local max here. The second derivative is positive here, we have local min here. Okay, let's analyze another one. This is an oblique asymptote. Oblique asymptotes I didn't mention as much. We can skip this example. Here we have point of inflection. Look at that. We have concave down and concave up. Concavity changed at this point, so it's a point of inflection. And we have another point of inflection because this is concave up, this is concave down, so this is a point of inflection as well. Let's see. What is this table? Let's understand this summary. This function is actually, as you will see, if it seems it's differentiable because there's no corner, etc. Then we call this curve as a smooth curve. It's a connected curve. This curve is going up and down, so it may rise and fall. This function, the first derivative is increasing, means that the first derivative is positive, means, if you remember the first derivative test, this function is increasing. So, and as you see, the curve could be wavy, but it's increasing. Look, it's going up and up, but in a wavy way. That's fine. This first derivative is less than 0, means f is decreasing and it can go down in a wavy way. And this is second derivative is positive. See, it is concave up, or it could be like concave up. It doesn't matter the function is increasing or decreasing, but second derivative is positive, means the graph is going to either look like this or like this. Okay, so the graph may rise or fall or both, no matter, either way. So second derivative positive means that. Second derivative is less than 0, means the graph is going to look like this or this. So you don't have any waves here, and you don't have any waves. Graph may rise or fall or both. Okay, rise, fall, or both of them. Second derivative sign changes at an inflection point. We talked about that. This is concave up here and then concave down, so point of inflection here. If the first derivative changes sign, we have, depending on changing from a positive to negative or negative to positive, it's going to be local max or local min. Changing from positive to negative, it's local max. Changing from negative to positive, it is local min. So this is the sign of first derivative is changing. Okay, this is the first derivative test here. If the first derivative is 0 at a point and second derivative is negative, which means second derivative negative means it's concave down, and first derivative is 0, this is the second derivative test, by the way. So graph is a local max. If the first derivative at this point is 0 and second derivative is positive, which means the graph is concave up, we have it, as you will see, local min. So these two expresses the second derivative test for local extrema. This is the first derivative test for local max, local extrema again. So this is the summary, and this is the end of 4.4.